this video we're going to talk about the relationship between molecular structure and the strength of an acid. So let's first consider binary acids. So remember, a binary acid is just a hydrogen covalently bonded to a nonmetal. And we could have more than one hydrogen. For example, H2S would be considered a binary acid because we just have hydrogens covalently bonded to a single nonmetal atom. When we're comparing the strength of binary acids, there are two things to consider. The first one is bond polarity. And so basically, the greater the polarity of the hydrogen Y bond, the stronger that acid is going to be. So in effect, the more electronegative the nonmetal, the more acidic that binary acid is going to be. And so if we consider ammonia, water, and HF, so these could all be generally considered having the structure of binary acids, and we see the electronegativity as we go from nitrogen to oxygen to fluorine, the electronegativity of that nonmetal increases. And so when we think about the strength of these, we would have predicted that HF is the stronger acid. And based on what we know about these compounds, that's certainly true. Right? We'd probably consider water not to be an acid at all, but we'd probably describe it as being neutral. And generally, ammonia behaves like a base. So as the electronegativity increases, we go from something that's basically a base to neutral to something that's definitely an acid. So when we have these binary acids, the more electronegative the nonmetal, the more acidic that compound is going to be. The other thing that we consider for binary acids is the strength of the bond. And the bigger the nonmetal gets, the longer and weaker the hydrogen nonmetal bond becomes. And the weaker the bond it is, the easier it is for that acid to give away the hydrogen, and so the stronger the acid is. Right? So as the nonmetal gets bigger, the acid gets stronger. And so if we compare three acids in the same column of the periodic table, we have HF, HCl, and HBr. And these are going down the periodic table. So as we go from fluorine to chlorine to bromine, the nonmetal is getting bigger, and we can see that the bond energy decreases, and we go from something HF is considered a weak acid, HCl is strong, and HBr is even stronger. Now we have these two different trends that may be competing, right? So we use the bond polarity when we're talking about nonmetals that are in the same row, like nitrogen, oxygen, and fluorine, right? So same row, use the bond polarity argument. If they're in the same column, then we would use the size argument. And if we have a mixture of things that would predict different things, that would be a hard question, one that I would not ask. Okay, so we've just talked about binary acids. Now let's talk about the other class of acids that we generally deal with in this course, and that's oxoacids or oxyacids. So these are acids that have polyatomic ions containing some number of oxygens and then having acidic hydrogens, balancing out the charge of those polyatomic ions. And so there are, again, two factors to consider when we're thinking about oxyacids. The first thing we can consider is the electronegativity of the central atom. The more electronegative the central atom, the stronger the acid. And so if we compare two acids that we're familiar with, phosphoric acid and sulfuric acid, if someone asked me to compare the acid strength for these two, I'd look at the central atom, phosphorus and sulfur, and look at their electronegativities. Sulfur is more electronegative than phosphorus, so based on that, we would predict that sulfuric acid is the stronger acid. And in fact, we know that's true, because sulfuric acid is classified as a strong acid, and phosphoric acid is classified as a weak acid. The other thing that we can consider when comparing the strength of oxyacids is the number of oxygens. The more oxygens connected to that central atom, the stronger the acid is going to be. So if we consider the family of these oxyacids, all with chlorine as the central atom, we can see that the Ka's, as we go from 1 oxygen to 2 oxygens to 3 oxygens to 4 oxygens, the Ka increases. And we know that an increasing Ka corresponds to a stronger acid. Right? And this also matches with information that we already know. We know that perchloric acid and chloric acid are categorized as strong acids. They have more oxygens, whereas the two compounds that have fewer oxygens, chlorous acid and hypochlorous acid, are weak acids. Okay, so let's look at a couple examples. So in each pair, we want to determine the stronger acid. So for HBr and HI, these are binary acids. They're not in the same row, but they're in the same column. So when they're in the same column, I want to use the size of the nonmetal. And since iodine is lower in the periodic table than bromine, iodine is bigger. That means the HI bond in hydroiodic acid is going to be weaker than the HBr bond in hydrobromic acid. So that means that HI will be the stronger acid. In the case of HCl versus H2S, again we have binary acids. Now they're in the same row, so I want to compare electronegativities. Chlorine is to the right of sulfur in the periodic table, therefore it is more electronegative, so we would predict that HCl is the stronger acid in that pair. Alright, now we have nitric acid and nitrous acid. These are oxyacids. The central atom is the same, so I don't have to worry about the electronegativity of the central atom. So the only difference here is the number of oxygens. So more oxygens means HNO3 is more acidic than HNO2. Our last example, we have HClO3 and HBrO3. Again, we have oxyacids. They have the same number of oxygens, so the difference here is the electronegativity of the central atom. Chlorine is more electronegative than bromine, so we would predict that HClO3 is more acidic than, or a stronger acid than HBrO3.